So you don't end up with a double bond in any of these spots. You end up with a double bond or a half of a double bond in all of these spots. It's actually 1 1/3 bonds instead of a true double bond. And that's called resonance. And that's because these electrons don't actually stay in one spot. When they have different spots that they could be in, they actually move between all the spots. And so all 3 of these are correct. All 3 of these are not correct. It's a mix of all 3. And so what we do with that, and I forgot to clear that. We say they're equivalent. And so all of those are valid Lewis structures. They're equivalent because they all have the exact same number of single and double bonds. All of them have 2 single bonds and 1 double bond. And when we have that, we say that they're equivalent resonant structures. Those are new words for us. So the word resonance, again, just means you could draw it more than one way. And then we say those different ways are equivalent if they have the exact same number of single and double bonds. That would be different than doing something like, if I did C3H4, this is one way of doing C3H4, and this is one way of doing C3H4. These are both resonance structures. They're both correct for drawing C3H4. But are they equivalent? Do they have the same number of single? And when I say multiple, it has to be the exact same. So this has 2 double, this has 1 triple. So these we would say are not equivalent because they don't both have 2 double bonds. They have different numbers of their multiple bonds. This has 1 triple, this has no triples, this has 2 doubles, this has no doubles. So these would be both resonant structures, but they're not equivalent. Okay? And so equivalent, again, means that they all have the exact same number of multiple bonds. They all have 1 double, and they all have 2 singles. Okay? So these are equivalent resonant structures. Okay?
So there's no really like wrong way to draw it?
Well, there isn't a wrong way to draw it, correct. And so a lot of times they're going to say, draw the different ones. And so when we have to draw the different resonance structures, we have to show that not only can it be here, but it could also be here, and it could also be here. So we draw all 3. And then we put arrows in between them to indicate that all 3 of these are correct.
Okay.
Okay? So for this, you wouldn't just draw 1. You'd actually draw all 3 if it asked for resonance structures, and you would do that. Now, if it just said draw a Lewis dot, that's fine, just draw 1.
Yeah.
But if it asked for the resonance structures, then you have to draw all the different possibilities for it.
Okay, that makes sense.
And so the actual structure is an average of all of them. And that's because these electrons, we said they're delocalized. They just can move around wherever they want, and they'll form all of them. And then the actual strength of the bonds is a little bit somewhere in the middle as well. And so what we do is we find something called bond order. And we can figure out the sort of, that it's not, that we don't actually have a double and 2 singles. What we have is something a little bit different. And I'll show you in a second. So we give single bonds a bond order of 1. So this is a 1, and this is a 1. We give a double bond an order of 2. So this double bond counts as a 2. So what is my total number that I have for bonds right here? So this is a 2 and a 1 and a 1. That equals a total of how much?
4.
4. This is 4. 1 double and 2 singles equals 4. So we say that that's a 4. And those 4 bonds are located in how many different locations?
1, 3, 2, 3.
So we say the total number is 4 over 3 different locations, and 4 divided by 3 is 1.3.
2.
30.
So this isn't really a 2. This isn't really a 1. All of them are actually 1.33s.
Mm.
So what it really looks like, it's sort of like n 1 1/3, n 1 1/3, and 1 1/3. Because again, this double bond is in all 3 spots, and it's being split between all 3 spots. So you have like a third and a third. And so that's a really weird concept or a really weird idea. But we find the overall bond order for the bond, and we say that it's not a 1, it's not a 2, it's really a 1.33 in all locations. And we'll practice that, okay? So you add up the total number of bonds, and then you divide by the locations. Okay. So that's bond order, is what that's called. So let's try one. Do you want to try drawing them out, or do you just want to do them together as a class?
Let's just do it together.
So we're going to do O3. What's my total number of valence electrons?
8.
What's 18? Yeah. 6 times 3. 18. And we're going to find the final bond order. So how should I draw this? I guess there's only one way to draw it, right? O bonded
Double.
to,
Oh.
bonded to a,
Oh.
no. So currently we have 2, 4, 6,
6, 8, 10,
and
12,
14, 16, 18. What's our problem?
It only has 6.
Yeah. This doesn't satisfy what rule?
Octet.
Yeah, that rule. Yeah. It needs 8 valence electrons. So what do we have to do if we don't have enough?
Double bond or triple bond.
Yeah, we start with a double bond first. So we'll start by getting rid of that, and I'm going to put in a double bond. And again, it doesn't matter what side I currently do this on. So 1, 2, so 2, 4, 6, 8. This oxygen's okay, and there's electrons. And 2, 4, 6. What do I have to do for valence electrons on this one? I mean, for lone pair.
You have to create double bonded too.
I just need one more lone pair. 2, 4, 6, 8, 10, 12, 14, 16, 18. Does everybody have 8? 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8.
Yeah.
So are we done?
No.
Why?
We gotta draw all the possibilities of what it can be.
So this double, so how many resonance structures do you think there are for this one?
We can do another one.
So there are a total of how many?
2.
2.
Good. So we're going to put this in brackets. I'm going to put an arrow between it. And this time when I draw it, what do I need to do different?
Do the double bond to the left.
Yeah.
You would really just be flipping it?
Yeah, you're just showing the double bond can be in this spot, or it can be in
No, there's
that spot. Yeah, that's it. And so, and then nothing else changes. This still has its 2. And then this still has the full 1, making sure everybody has 8. So again, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And our total electrons, 2, 4, 6, 8, 10, 12, 14, 16, 18.
Mm-hmm.
So those are our 2 resonance structures. Then it says find the bond order. So what do I do now?
Find the number of bonds.
So what does a single bond count as?
One,
One,
1,
And a double bond counts as a?
2,
two,
So that's,
3
and
over 2.
we'll say this is our bond order. And so 3, and how many spots are they located in?
2.
Two. So what do I get?
1 by 5.
So really,
Wait, where did you get the 3?
There's 3 bonds.
Oh.
double
right.
counts as 2, and a single counts as 1. That's a total of 3. And they're located in 2 spots. So instead of a double and a single, what's really existing?
The half.
5.
They're really a 1.5 in each spot.
Mhm.
Okay.
Would
So
the
that-
other side be the same thing?
Yeah, exact same thing. They'll always have the same bond order because they're
Okay.
really just the same.
So these are equivalent, right?
These 2 are equivalent. Yep. So these are 2 equivalent resonance structures because they both have a double and a single.
Single.
Okay with that?
Mhm.
Yeah.
Then, and so again, there's what we came up with. And we say they are equivalent because they have the same number of single and multiple bonds. They have each of 1 single and 1 double. Non-equivalent are going to have different numbers of single and multiple bonds. And so it's a little bit harder because both of these are correct, right? But for non-equivalent, we have to figure out a way of figuring out which one is correct because there's some crazy ways to draw things and to get all the valence electrons on. And they're a lot of times they look insane and they're nowhere near being right. Okay. And so we use something called formal charge. And formal charge helps us determine which non-equivalent structure is the better structure. Which one's the better Lewis dot for it. You still have to satisfy the octet rule, but we have to do something called find formal charge. And I'm going to show you 2 ways of doing it. One way you won't find in a textbook ever. One way you will find in a textbook. So the rules for this, and we'll come back to these, we're going to have to revisit them. You want to get a formal charge as close to 0 as possible for your right structure. So if you're comparing 2 structures, you want to find the one that has the most zeros on it. The formal charges, when you add them up, must equal the overall charge of the molecule. So if it's a big -1 outside those brackets, when you add up the formal charges, it must equal a -1. And then if 2 are really, really close to each other, you want the negative charges to be on the most electronegative atom. So when we draw something, lone pairs belong to the atom. Shared electrons, if you have a bond between 2 things, each of them get 1 of the electrons. So I'm going to show you 2 formulas here. So the first way is you add up the lone pairs and half of the shared pairs, and you subtract them from the total number of valence electrons. That's the first way. The other way is formal charge is equal to how many they should have minus how many they do have. I'm really bad at writing with this. Should have minus the amount they do have, or that they just have in the picture. Okay, and we'll do both ways. And you sort of figure out what works best for you. Okay. So let's try one. I think we're up to trying one. So we're going to find the formal charge for everything here. Okay. And I'm going to start by doing it the textbook way. So the way you do it is I have to find the formal charge of every atom in the molecule. And it looks like it's really long and tedious, and it is a little bit at first. They go really, really fast after that, though. So how many total valence electrons does Cl have? Sorry, lone pair electrons does it have that aren't making bonds? So it has 2, 4.
Or
6.
Then because these are really 2 electrons, a single bond, we say 1 belongs to the chlorine and 1 belongs to the phosphorus. So chlorine has how many valence electrons?
7?
7 minus 2, 4, 6, and half of the bonded pair. So one of these is
So,
7.
7.
The 2, 4, 6, and only 1 out of the bond. 7.
oh,
So the formal charge on this Cl is we put a little 0. Okay. We'll go left on this. Anything different with this one?
No.
Nope. 2, 4, 6, and 1 of the single bond. So 7. 7 minus 7 is?
0.
Anything different here?
Mm-mm.
So it is?
7.
What about oxygen?
isn't it the same?
Supposed to have
No,
Oh no.
2, 4,
it's 7 minus 6.
no,
So
you
valence electrons, how many? So it's always valence equals lone pair electrons plus half of the bonded or shared ones.
Also 7.
So our valence electrons for oxygen are how many valence does it normally have?
No, 6. 6.
6 minus 2, 4, 6,
Plus
and one of these. So 6 minus 7 is?
negative.
-1.
So the formal charge on the oxygen is -1. And what is the formal charge on phosphorus? So what's the valence electrons for phosphorus?
Phosphorus.
Supposed to 5 usually.
5. And so how many does it get from each of these shared?
1,
Gets
One.
1. So 1, 2,
1,
3, 4,
so 5 minus 4, the charge on phosphorus is a?
1.
1. Positive 1.
So remember, when you add up all the formal charges, they have to equal the overall charge of this molecule. Do we see a charge given here?
No.
So we know
No.
its overall charge is?
0.
0.
So 0 plus 0 plus 0 plus 1 minus 1 equals
0.
0. Okay. So that's how we find formal charge. That's
Should have.
the second way. The second way that we do this is how many they should have minus how many they have. So should have, should have minus how many they have. So how many valence should chlorine have?
7.
How many does it have?
7.
So
7.
this is
0.
7 minus
7. 0.
7 minus 7.
0.
Phosphorus should have 5. It has,
It has 4.
Minus 4. Plus 1.
oxygen should have 6. It has 2, 4, 6.
7.
That's the other way of doing it. Okay? So should have minus how many it has. Both give you the exact same answer. Okay. That makes sense, how you found formal charge?
Yeah.
So we then, and I'm really just going to introduce it today. Oops. So yeah, we already did that. Blah, 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 blah. Sorry. Man. So let's evaluate these 8 that already have formal charge found for you. And let's determine which one of these is the right one.
Mm-hmm.
So just take a second and look at all of them. All right, we have a chance to look at them all.
Yeah.
Yeah.
So if I said draw XeO3 with 26 valence electrons, these are all ways of getting 26 valence electrons.
Mm.
These are all different resonance structures. But are they all equivalent?
No.
They're not equivalent because they all have different number of bond types, right?
This thing.
Kelvin, lower music. Because when
20
in
is
doubt, it's always Kelvin.
Whatever
don't-
music that is, you turn it off.
So our rules are, again, if we go back,
It has.
we want to find the one that has the formal charges closest to 0. There's a couple that have the same total numbers. We want to find the ones that have the most negative on the most electronegative. And we have to make sure that the sum equals the overall total charge of the molecule. And in this one, the overall charge of this molecule is how much?
0.
Yeah.
So 3 minus plus 3 plus 1. Does this equal 0 overall?
Nah.
No.
No, this is a plus 1, plus 3, and 2 minuses.
No.
Does this one equal 0 overall?
No.
Does this one?
Yes.
Okay. So that will be our first one that maybe we can consider. We're going to say no, because these don't even equal 0. What about this one?
No.
This one?
Yeah, we could
Yeah.
consider
Yes.
considered. No. Yeah.
So we've narrowed it down to 4.
Mm-hmm.
And so we, again, want to pick the one that has the formal charges are closest to 0 overall. Is there one that has that?
One that is 0.
Yeah.
Yeah. Which one?
The last one.
Last one. This is the one that has most of its formal charges at 0. In fact, all of them are. So this is our right one. It makes sense because xenon has 2, 4, 6, 8 valence electrons. All the oxygen have 8. We know oxygen wants to make 2 bonds,
Mm-hmm.
and they all do. And we know xenon. Normally we say noble gases don't make bonds, but here's an example of where it does.
Mm-hmm.
Yeah.
So I told you, I think in Chem 1, they don't make bonds. They do. It's just not super common.
All
I
right.
thought it was the last one too,
Good.
because it was a noble gas.
Yeah. And so we don't want a positive charge on xenon, right? It's a noble gas.
Right.
We definitely don't want a +3 charge on it. We don't want oxygens being +1 right?
Mm-mm.
We know oxygen are normally negative charges.
Negative.
So through evaluating of all these, we can narrow it down out of 8 of them to which one it is. And that's something that they can ask you to do. And so let's do one more, and then we'll wrap up for today. So let's go through and find some formal charges. Do you want to use the valence minus lone pair plus half, or do you want to do should minus have?
Should minus
Should minus have? Okay. Oxygen should have how many?
6.
6,
How many does it have here?
7,
7.
2,
Oh,
4,
it's-
6, and half of this is 7. So that's a
-1. -1.
Okay.
-1.
Dang.
-1.
And then 1,
Should have
That's
6
4.
as
4.
4 so 2 plus 2.
should have 6, and it has 4. So plus 2. When I add these up, does it equal a minus 2?
Yeah.
1, 2, 3, 4.
Yes?
Yeah.
Yeah.
2 minus 4 is minus 2.
Mm-hmm.
Over here,
Should have 6 has 6. So that's 0.
so again, we're doing should have minus how many it has. Is going to equal our formal charge. So it should have 6 because it's oxygen. It's in 6A. It has 2, 4, 1
5.
of these, and 1 from here.
And the other one.
6.
And so its formal charge is
0.
And that's 7
Minus 1.
1.
yep 6 minus 2, 4, 6, 7. So minus 1.
Yeah.
So we
Minus 1. And then
That's 0.
and then it's
That's
Should have 6. It has 1, 2, 3, 4, 5, 6. So 0.
that's 0 too.
and then
Yeah, when we add, it is negative.
Yeah, you
negative
too.
1 and negative 1 is.
Negative 2.
2.
So nothing crazy in this one, right? Not like the last one. Both of them look reasonable. Which one is the better structure?
The other one.
Left or right?
Oh, left.
Left?
Right.
Yeah.
Doesn't oxygen tend to make double?
So again, we always want to find the one that has the most what?
0.
Zeros.
Also be right.
So it'd be right.
This one has the most zeros. And then out of them, in this one, is sulfur a positive charge normally?
Mm,
No.
So it shouldn't normally be a positive. And oxygen should be negative. So overall, it's going to be this one because it has 3 zeros.
Mhm.
Sometimes when you look at them, they're going to look like there's some crazy ones. And I was going to do breakout groups and make all of you go through and do one of these, but I'm not going to. And so this is just asking which one is most likely. And so looking at them, why do you think you can rule some out right away? Like, what looks wrong in this first one?
H has 2 bonds.
Yeah. H is making 2 bonds. We can automatically say there's no way this is the most correct one.
Along with the
And
second one.
B, right?
B.
Is it D?
So we can eliminate that, and we can eliminate
That one.
that.
Also C as well, because F is also making 2.
And so it's a matter of which one of these is most correct. But remember, boron tends to make how many bonds?
Boron
Two.
tend to make two.
3.
3.
Three.
So boron tends to make 3. So that's good, but the F is not really good.
Yeah,
And
it's
here-
making 2 bonds.
Here,
Nice.
boron
Making-
makes 3, but it has 4, but
Yeah.
the F's are good. And so it comes down to deciding
Which one?
which one is right on this one. And so this one was tricky because they don't put lone pairs on. And I'm assuming, I haven't actually even solved this. I'm assuming they're supposed to be lone pairs on all these. Just put on, and I want you to assume that. And you could figure it out just from the formula. You could add up the total valence electrons, right? Our formula for this is like NH3 BF3. What is that? 5, 3, 3, 21, 32. Is that right?
Yeah.
Yeah.
I know you already know without me putting all these on here. So I'm interested to see if they included lone pairs on this one. I'm going to guess that they did. So let's find formal charge. Let's find them real quick. So the H's, they all have 1, -1, so all of these are.
0.
N should have 5, it has.
4
So it's plus.
plus 1.
N should have 7, it has 2, 4, 5, 6, so this is a +1. Same thing here. What's this one? Actually, this one's not the same.
Isn't it 0?
Yep. This one,
0.
0. And I have to count to see if there's supposed to be these here. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 12. They are supposed to be there. Okay. So boron,
Boron is supposed to have. Is it boron 2? Boron
supposed to have 3.
3.
And so that's
2.
1, 2, 3, 4, 5. So -2. So overall, does this equal 0? +1, +1, -2.
Yeah.
Oh, yeah.
Down here on the bottom. So 1 - 1, 0, 0, 0. What's N?
And it's supposed to 5. Is it +1?
F?
0. 0. 0.
And B?
-1.
So which one do you think is the more correct?
D.
D. Why?
It has
Has the most 0.
Has the most zeros, and F should never, ever, ever be
Yeah, +1.
+1. Yep. So Kelvin's initial observation that F is making 2 bonds affected that. F's always your most electronegative. It always is going to be a negative, if not a 0. Okay. So your answer for that would be